classmates, the output voltage of a proportional operation circuit has a proportional relationship with the input voltage. That is, the circuit can perform proportional operations. Proportional operation is the most basic type of operational circuit. It is the foundation for other various operational circuits. According to different input signal connections, proportional circuits come in inverting input, non-inverting input, and differential input proportional circuits among other forms. Let's now move into the study of proportional operation circuit testing. The teaching objectives of this section are 1. To be able to analyze inverting proportional operational circuits. 2. To be able to analyze non-inverting proportional operational circuits. Let's first take a look at what an inverting amplifier is.
Inverting amplifier. It refers to the operational amplifier in electronic circuits. There are in-phase and in-phase input terminals. Polarity of input and output terminals. If they are of the same polarity, they are in-phase amplifiers. And the polarity of the input terminal is opposite to that of the output terminal. It is called an inverting amplifier. The inverting amplifier circuit has the function of amplifying the input signal and inverting the output. Operational amplifiers have the following characteristics. When no power supply voltage is applied to the output terminal, positive input terminal and negative input terminal considered to have applied the same voltage. That is to say, it can be considered as a virtual short circuit. So, when the positive input terminal is 0 volt, the voltage at point A is also 0 volt.
Let's analyze in detail. The inverting proportional operational circuit. The circuit is shown in the figure gesture. The signal is input from the inverting terminal N. The non-inverting terminal P is connected to the ground through resistor R2. The feedback resistor RF is connected across between the output terminal and inverting terminal. Voltage parallel negative feedback is introduced. This makes the operational amplifier work in the linear region. The characteristic of the feedback here is the input signal generates the output signal. The output signal is fed back and affects the input signal. The two form a closed-loop system. This enhances the stability of the system, or enhances the output effect of the system. In our learning, working, and life, we all need to use feedback from the outside world to continuously improve ourselves and improve personal literacy. R2 is called the balancing resistor. The value of R2 is equal to the parallel resistance value of R1 and RF. It ensures that the two input terminals of the integrated operational amplifier have equal external resistance when static. This is used to improve the integrated operational amplifier, the symmetry of the differential input stage. Even if the static potential of the two input terminals is balanced, to improve the suppression capability of common mode signals, improve the common mode rejection ratio. The method for finding the balancing resistor, let UI is equal to 0, then UO is equal to 0. At this time, the total resistance from the inverting terminal to the ground is the value of the balancing resistor we are looking for. using the ideal operational amplifier working in the linear region has virtual short U plus is equal to U minus. Virtual break I plus is equal to I minus is equal to O. Two important conclusions. Analyze as follows. Since I plus is equal to 0, then U plus is equal to UP is equal to 0. And because U minus is equal to U plus, so U minus is equal to 0. That is, the potential at the inverting input terminal N point is approximately equal to the ground potential, but it is not ground, so it is called a virtual ground. The inverting terminal N is the virtual ground. It is an important characteristic of the inverting input operational amplifier. An important feature of the circuit since I minus is equal to 0, then I1 is equal to IF. That is this formula. In the above formula, U minus is equal to 0. From this, we can obtain this formula, or expressed using the closed-loop voltage gain as this formula. The above formula indicates that UO is inversely proportional to UI. The negative sign indicates that UO and UI are out of phase. The proportionality coefficient is independent of the parameters of the integrated optional amplifier itself. It is only related to the parameters of the externally connected components. If Ri is equal to Rf, then Ui is equal to minus Uo. That is, Uo and Ui are equal in magnitude and opposite in phase. At this point, the circuit is called an inverter or a phase inverter. Let's go through an example problem to illustrate how to calculate the output voltage. The circuit is shown in the figure. Given R1 is equal to 1.5 k ohms, AUF is equal to minus 20. Find the value of RF and the value of UO when UI is equal to 0.2 V. From the previous conclusion, we know when UI is equal to 0.2 V, we will not only calculate this, but also test the inverting proportional operational circuit. The left figure is the basic application experimental circuit board for operational amplifiers. The integrated operational amplifier used here is the LM358 chip. It has two integrated operational amplifiers inside. We are only using one of them here. On this experimental circuit board, according to the right figure, the inverting proportional operational test circuit. Select the resistors and connect the wires. It can achieve the inverse proportional operation of UO and UI. Now, let's start the circuit test. Set the input voltage to be 0.2 V. Before the experiment, clearly identify the position of the pins of the operational amplifier opponents. Avoid averting positive and negative power supply polarities. Avoid reversing and short-circuiting the output terminal. Otherwise, it will damage the integrated block. Firstly, our board has already connected. The positive and negative 5V voltages used inside and brought them out. The power supply for the chip and the voltage divider network does not require us to connect any more wires. Just plug the board directly into the experimental platform. This way, the power supply of the board is connected with a power lines on the experimental platform. We need to adjust to an input direct current signal of 0.2 V. A resistor voltage divider network is used here. We connect its output terminal to a digital voltmeter. Turn on the power on the experimental platform. Adjust this potentiometer so that the output for is 0.2 V. Turn off the power. Then connect the experimental circuit according to the right figure. The output for of the resistor voltage divider network is connected to 0.5. The non-inverting terminal 8 is directly grounded. The 13 end of the feedback resistor R3 is connected to the inverting terminal 6. The 14 end of R3 is connected to the output of the operational amplifier. After we have completed the wiring, how do we determine if the wiring is correct? Here, the input terminal resistor is 10 k-ohms. The feedback resistor is 100 k-ohms. The amplification factor is 10 times. Then our output should be around -2 V. We connect the digital voltmeter to the output of the operational amplifier. If the output is correct, it indicates that the wiring is correct. After carefully checking that there are no errors in the wiring, connect the power. Measure the responding output voltage. The experimental data is correct. Let's now look at the non-inverting proportional operational circuit. The circuit is shown in the figure. The input voltage UI is connected to the non-inverting input terminal. RF is still connected between the output and the inverting input terminal. Voltage series negative feedback is introduced. The operational amplifier works in the linear region. In the figure, in the balancing resistor, R2 is equal to the parallel resistance value of R1 and RF. Using the conclusions of virtual short and virtual break, analyze as follows. Since I plus is equal to 0, so U plus is equal to UI. And because U minus is equal to U plus, that is, U minus is equal to U plus is equal to UI. Since I minus is equal to 0, I1 is equal to IF. That is, this formula. Substitute U minus is equal to UI into the above formula to obtain. Expressed with the closed-loop voltage gain as this formula. The above formula indicates that UO is directly proportional to UI, compared with the inverting proportional operational circuit. Its voltage amplification factor is always greater than or equal to 1. UO and UI are in phase. If R1 is equal to infinity in the figure, or RF is equal to 0. From the above formula, it can be seen that UO is equal to UI. At this time, the circuit is called a voltage follower. As shown in the figure, this type of voltage follower has a very high input resistance and a very low output resistance. Its performance is much better than that of discrete component voltage followers. The following performance is very stable. In the non-inverting proportional operational circuit, since U minus is equal to U plus is equal to Ui, therefore, the inverting input terminal in is no longer a virtual ground. At the same time, there is a common mode voltage at both input terminals. Therefore, in the application, it is necessary to avoid the virtual common mode input signal in the circuit, exceeding the maximum common mode input voltage allowed by the operational amplifier. Otherwise, the operational amplifier cannot work properly. We will now test the non-inverting proportional operational circuit. The left figure is the basic application experimental circuit board for operational amplifiers. On this experimental circuit board, according to the right figure, the non-inverting proportional operational test circuit, select the resistors and connect the wires. It can achieve the direct proportional operation of UO and UI. The input voltage here is still a 0.2 V direct current signals. Then connect the experiment circuit according to the right figure. The output 4 of the resistor voltage divider network is connected to port 7. Port 5 is directly grounded. The 13 end of the feedback resistor R3 is connected to the inverting terminal 6. The 14 end of R3 is connected to the output of the operational amplifier. After we have finished the wiring, how do we determine if the wiring is connected? According to our circuit diagram, the output voltage, this formula. Here, the input terminal resistor is 10 k-ohms. The feedback resistor is 100 k-ohms. Substitute and calculate that our output should be around 2.2 V. We connect the digital voltmeter to the output of the operational amplifier. If the output is correct, it indicates that the wiring is correct. After carefully checking that there are no errors in the wiring, connect the power and measure the responding UO. The experimental data is correct. Classmates, through circuit analysis, we have obtained the relationship between the output and input of the inverting amplifier and the non-inverting amplifier. The relationship between the output and input. Further, through the connection of the circuit, we carry out the test of inverting proportional operational circuit and the non-inverting proportional operational circuit. This further verifies the functionality of the operational amplifier. It enhances the ability to recognize circuit diagrams. The content of this class ends here. Goodbye.